Hey everyone. I'm Siddath. I work at Reality Engines, and I am visiting from Austin here in San Francisco for a couple of days. Well, primarily here to talk to you guys. I'll tell you more about myself because it's in some ways relevant to the talk also in a couple of slides. But I just want to start with a little, shall we say, caveat. She mentioned AI paper, and the talk says distributed deep learning, and I'm always a little ambivalent about these distributed X kind of talks because they tend to be neither about X nor about distributed, because the reason we distribute things is not to improve X. Like distributed deep learning doesn't really improve the deep learning. It just makes it go faster or allows you to tackle bigger problems. So the part of there is deep learning in this talk, but fair warning upfront. A lot of it is about how we got to our current place for distributed computing and what applies in the deep learning space, what applied before, what doesn't work from before, and things like that. To explain sort of the subtitle of this talk, let's see if this is on, maybe. Hang on, let me just see if this is working. Oh, there we go. I'm just going to use the keys. Okay, so this has always been like a popular XKCD release with me. This one is actually not the original. The original one was for software developers, and they were waiting for compiling. I think now this has been updated for data scientists, and this is what we commonly hear, right? So distributed compiling, distributed anything, distributed deep learning or whatever is basically to make the train iterate cycle faster so that we can try more ideas or get stuff done quickly. It doesn't necessarily change what we're doing. Mostly we have to try and make sure that whatever we distribute trains the same way as it would on a sequential processor. But it does enable us to do more, right? So in that, guys, I've seen many different sort of versions of distributed. So to tell you a little bit about myself, right? So my background was I actually did my PhD in physics, and let's try going back once and forward, see if it sticks around. During my PhD, one of the things I studied was the property of metal alloys. For that, we used supercomputers for computing, the structure of alloys, and that was distributed computing. It's just all of the distribution was within one big computer. When I joined Google, it was another. I worked in search ads targeting, newspaper digitization, a bunch of stuff. I also actually Bindu probably will. She always tells people that the most useful thing I've done is apparently Google BigQuery. It's apparently also the only useful thing about Google's cloud, but I think she's being a little tongue-in-cheek. But Google BigQuery was distributed analytics, and then when I worked in futures trading, we used distributed training for finding trading strategies, basically scaling up trading. Actually, a lot like what we do for deep learning. Amazon had its mix of distributed computing where we did OR type problems or predictive modeling, which is more classical machine learning. And now here at Reality Engines, we do deep learning, hopefully enough of deep learning that we really need distribution, right? So that's the key thing. You want to do enough of it that you need distribution. So through this whole cycle, through these different sort of types of problems, all of which have had some form of distributed computing applied to them. One of the things I was looking back as thinking about this talk, I realized that as consumers of distributed platforms or we use MapReduce or Spark or whatever TensorFlow for doing distributed deep learning. We often forget that those frameworks very much emerge from the constraints of the hardware of the time, whatever sort of where hardware and different components in the hardware stack are at the time. And it's quite interesting to think how significant some of these differences and properties are and how important they are for the design of the appropriate framework, right? So I don't know if you guys have seen this graph on the what would be your right. But it was a fascinating one the first time I sort of saw it, and you kind of know the numbers in your head, but you don't think of it in this scale. So the graph shows timing in basically the computing stack all the way from CPU cycle to like network transfers, but scaled up to like more like human time scales, right? So like if a clock cycle in a CPU, the time to do like one addition cycle or something was 1 second, the time to go back and forth between like across East Coast or West Coast is a year. It takes a year to do that. So so when we're thinking about this, like we think about this in our human processes, like roughly like what, like an action that takes a second is something like swiping a credit card, right? Like we might spend a second swiping a credit card. If it took a year for that credit card to actually be approved or denied or whatever, we would have to completely rethink how we design the payment process, right? If you use cash instead of credit cards, you can't build a process around those kind of differences. And a lot of that also applies to these systems underlying these distributed systems when people come up with these various designs for frameworks for distributed computing. And another one is it changes a lot over time. I was doing some history deep diving, and I saw like gigabit Ethernet, the standard was finalized in like 1998. And I think like the data centers that are right now being built by Google and so on the box, they have 100 gigabit inline. So that's 2 orders of magnitude change in about 2 decades. So it's really, these things change a lot, and they're very different. So so going back to my sort of like first sort of like experience with distributed computing, right? So the problem was to compute the structure of alloys, as I mentioned, and like roughly, it's quite simple to describe the problem. You have all these atoms sitting in some kind of crystal structure, and what you want to do is find out the resting state or the resting place of each of these atoms. And so you put them randomly, and then you calculate the forces, and you move them about according to those forces until they find their final place. There's some fancy physics. The fancy physics turns into a bunch of simple nested for loops. There's a lot of like numbers shifted around, keeping track of indices just like we do today, same thing. Then a matrix inversion, some matrix multiplication, and your answer comes out. The reason you do distribution is like each of these loops have to be run for each atom. There are a lot of atoms. So what we do is we carve up the space, we assign a few atoms to each cell, we let one processor decide what to do about that, run the computation for that cell, and then exchange some data with its neighbors and run iteration by iteration and kind of crank through the data. So interestingly, I would say that this seems like a real aside, but this is probably, for the next few slides, this is about the closest we are to like what current deep learning infrastructure looks like. So there's this theme of like sort of coming back, like things going in and out of fashion, or sort of like what's popular, right? So the things that seem to govern this govern the choice of like platform or paradigm that we use for computing is, given the problem type and the hardware, we have a couple of these ratios, right? So like one of the things about this like molecular problem is there's a lot of computation time compared to the amount of data that has to be exchanged. You have to like do a lot of calculation, run a lot of for loops, move a lot of memory within the core before you need to exchange stuff with your neighbors to proceed. The input is small. The input is just described by the positions of each of these atoms and what kind of atom it is. For maybe like 1,000 atoms or something like that, it fits in like a small text file, no problem. But the amount of compute you have to do on that to actually get an answer is huge. Again, a bit like deep learning, where we can describe the model fairly compactly, but once we have to start like computing it, it has all of these like gradients and weights and so on. And then another interesting one that I feel like keeps coming up is the failure mode, like how much we have to worry about like some subset of the computation failing. Like, do we have to like work around transient failures? Do we have to worry about like pieces of it failing and being able to recover? A lot of I think like a lot of the frameworks do a lot of work to get through that. And so then so that sort of like sets the stage for like MapReduce. So after I graduated from college and went to Google, like I very quickly ran into MapReduce, one of the first things first pieces of technology exposed to, and it was eye-opening. It was very impressive. It allowed me to like very quickly do stuff on web scale data, and in fact, I think it was so successful that like following Google's like release of the paper and its adoption by the open source community, I think a lot of like a lot of the approaches to distributed computing have kind of been forced into the MapReduce framework, whether appropriate or not, but it's just such a convenient, such a powerful, such a successful framework that it's kind of become ubiquitous. The picture for the hammer for the nail is kind of like an allusion to that, saying that, I think we got into the stage where like MapReduce was so good that everything began to look like a nail. We tried to like turn every problem into MapReduce, often sometimes making things harder than they needed to be. And I think this is partly because we kind of forgot like when MapReduce came about. So MapReduce came about when there's web scale data. Google had to index the web. It had to like move these giant amounts of input. So the input sizes were huge. Just the time to like pull the data into the machines was like enormous. Everything was spinning disks. We had like this, the data transfer speeds were slow because they're coming off of disk. The data center networks were slow. Like you had to worry about things like locality. Was your mapper running close to your data? Was your reducer running close to your mapper? Because you couldn't actually move data across racks. You had to worry about racks and whether you're in the same section of the data center or whatever. And MapReduce took care of all of this for you. And it also took care of cheap hardware. So Google famously was very bargain basement in its initial set of like computers that it built. There were failures all the time. They didn't have good isolation, so your jobs got stomped on by other jobs. And so whatever distributed compute framework had to like work around all of these, and MapReduce did it exceptionally well. And as a result, it worked everywhere. So I have to spend a little bit of time like talking about BigQuery, and it's my experience with it there. So one of the internal service that first predated BigQuery was a service called Dremel, which people got tired of waiting on MapReduce to do simple queries on logs. And so there was this internal service built. It was fairly basic, but it allowed simple queries to very, very quickly be executed. But what's interesting to me is that even in that, I think the designer of that thing was very much inspired by MapReduce. Like if you see the service, even though it was set up as an online service, and sort of an online service for analytics with like long-running services, it was designed very much with the MapReduce computation in mind. How it was organized was there's these like leaf nodes that actually had the data also to achieve the locality. They could run operations like a mapper. So in the SQL world, that's effectively like the select and project that runs in the mappers or the leaf nodes. There's an aggregation layer there that acts as our reducers. That's where the group by operations happen. And then finally, the answer is returned at the root, and maybe it does a total like sort or whatever at the end. But the point being, like, so much was like defined by MapReduce that, like, even as new frameworks came about, this strongly influenced by MapReduce. So then so there was a significant change in networking at Google. In fact, if you see like now, like most, in open source Hadoop code, but all of like Google's MapReduce code and all that basically got rid of like locality or concerns about like moving data between nodes. The innovation was, the network engineers over time got to like petabyte scale bisection networks. And to explain so a petabyte scale bisection network allows 100,000 computers to talk to each other at 10 gigabytes per second, symmetrically. So that means like you can, every computer can talk to every other computer with data coming in and out of it at an aggregate throughput of 10 gigabytes per second. It doesn't matter where in the network you are. Like you can be on the same rack, you can be across the data center floor. So this is very freeing. Like suddenly you don't have to worry about like being close to your data. You don't have to worry about moving data between nodes. You can come up with completely new architectures. And in fact, externally, like you would say Spark is something like this, where like you bring up a set of workers. The workers both do computation and they host data. You don't have to write data to the disk all the time. You can actually move data between nodes. You can make a plan that involves shuffling data across nodes and so on. And so you have these much more dynamic architectures. BigQuery's internal engine also now follows this model where you just have a pool of workers, a pool of planners, and the planners kind of like schedule work on the workers, and they know where data lives on the workers, and they pass. The workers talk n squared between themselves. They're not trying to talk up a tree. They can talk to each other and like shuffle data and like execute complex plans that have joins and so on. So networking, I would say at this point got to the point where it was ahead was keeping up with the CPU core, right? So like just to go through some numbers, like our cores run at around 1 gigahertz now. To do some kind of simple processing on a record, like do some filtering, addition, subtraction, maybe a trigonometric function or something, you're looking at about 10,000 cycles. Cycles add up quickly, decoding, all of these things take time. And so, core can be pushing out 100K records per second. 1K is a fairly large record for an encoded record. So that 1K record, you have to move out of the computer. That's 100 megabytes per second. And if you have like 100 cores, 64 to 128 cores on like the big boxes, you need to move about 10 gigabytes per second off of the box, and you can do that. These networks were able to keep up with that, and so now you could like really sort of like treat the data center as like one big computer. You could read data off of disks that were remote. Another really interesting innovation that I think some people might be familiar with is actually networking like InfiniBand and so on, right? So that basically takes the CPU core out of the networking call stack. So you don't have to spend any CPU to actually move data out of like your SSDs or disks and so on. So all of these things basically made it much easier to program the data center kind of as a computer, right? And so now we're at we were at the place where now networking has like caught up with CPUs and all seems good. And then we, in the past decade or so, deep learning has exploded, and GPUs have exploded. And GPUs have like again moved this balance back the other direction. So the numbers are like actually mind-boggling now, right? So this device, this is the Tesla V100, you can put 8 of them in a box. Each one of them does apparently 100 teraflops. The number was like really surprising because when I was working at that supercomputing center in Pittsburgh, they recently installed this computer called the Big Ben, which is the Cray XT3. And I think the Cray XT3 as a whole had 10 teraflops of throughput, like the whole Pittsburgh supercomputing center. This, of course, it was a little bit more flexible. It was a CPU, so it wasn't like limited in the way a GPU is in the kind of computation you can do. But a teraflop is a teraflop, and like we have to do a lot of matrix multiplication, so it works well. But the other thing that changed a lot is like, when you have 8 of these in a machine, I checked on the web, like the price of a machine with 8 of these is $100,000. You don't worry about failures. Like if your $100,000 machine is like crashing on you, you have other problems. Like you don't have to, it's not just your model training that's gone. Like you've just lost a $100,000 piece of like equipment. So these things don't really crash. You don't worry about failure in the same way. The domain for like execution is much smaller. So it's again much more about like just raw compute going really fast and not having the bandwidth to like get the data between cores, right? So this is kind of like this pattern that I've seen like throughout. Like you have, like sometimes you're in a compute constrained world, sometimes you're in a transfer constrained world, and I think deep learning is in a transfer constrained world. It's like hard to scale deep learning outside boxes now. We can scale it across GPUs, but not outside boxes. So, coming to like now specifically distributed deep learning. So probably, people familiar with this thing know that there's like this kind of fork between like model parallelism and data parallelism. And mostly people work with data parallelism, as we will see why. Model parallelism is interesting. Like there are good reasons to have models split across GPUs, because sometimes really large models don't fit on a single GPU just for memory constraint issues and so on. NVIDIA has done a lot to like make the inter-GPU transfers like really fast, so you can make it work. But it's actually very often not really model parallel. So the reason it's not model parallel is like if you have your model split across 2 GPUs and one layer depends on another layer during like forward propagation and backward propagation, you don't have the GPUs all fully utilized. They're not running concurrently. There are ways to do it, like some like in some CNNs, in some model designs, you can actually have parts of the model evaluating concurrently in the forward and backward passes, but it's not easy, it's not that common. So I think it's an interesting thing, but it's not the area I'm going to focus for sort of the rest of the discussion. I want to focus on the data parallelism thing, right? So data parallelism is is fairly easy to like, as in the opportunity to exploit it if you can do it and protect the convergence of the model and so on. So the couple of like, okay, so the thing that's emerged here, like for data parallelism, like the primitives that are showing up are very much the primitives that were popular during the supercomputing days, right? So it's some kind of like MPI style interface where you have these large buffers of memory spread across memory that's like relatively far away from each other. It could be on different GPUs, often it is on different boxes, and you have to exchange that memory between them. So there's these MPI primitives like reduce all or scatter gather, where it coordinates the efficient dispersion and collection of memory between these nodes, because we are now in a transfer bottlenecked world, so we have to do this very carefully. And NVIDIA, NCCL is NVIDIA's improvement over OpenMPI's offering. And then there are frameworks like Horoward, which is, I believe, it's an Uber released open source project, which utilizes some of this to run distributed deep learning algorithms. So I was going to talk through a specific example, a model that we built at Amazon. I won't go into too many details about what the exact problem is, because I don't know how much of it is like Amazon, sort of confidential, but I can tell you the rough details without any issue. So the problem was to build a model that predicted some properties about deliveries in certain destination, like by destination. So we wanted to understand properties of like what would happen to deliveries going to destinations at a given time, on a given day of week, a given type of delivery, size, package, those kind of things. So we needed a model to predict that, there's a fair mix of data. You have a lot of continuous variables, a lot of like categorical variables that describe like the properties of the shipment, the nature of the delivery, and so on. And one of the key features, as you can imagine, is where it's being delivered, right? So zip code is a really important feature. And we used a standard sort of embedding encoding for the zip code. And in the US, that's about 50,000 zip codes that you need to represent. And it's all pretty straightforward. And we trained a model that had fairly good accuracy. So there was not a problem like training the model. You were able to build get reasonable fidelity and all that. It just took time. So it took about 30-ish hours to train the model on data. One of the reasons is the input data set was very large. Amazon ships a lot of items. You have to like train over a reasonable number of them to get enough to learn over the space. So there's a lot of data, so just chewing through all of that data takes a lot of time. The model itself is not like particularly large, it's more about the data size that you have to learn over. So natural thing is, it's annoying to have to wait a whole day, it's hard to iterate the same thing, long coffee breaks, people taking a lot of time doing things they shouldn't be doing while this model was training. So we tried to speed it up. And that, unfortunately, was what the speed up looked like. So we didn't actually use like Horoward. We didn't use a framework as such. It was a fairly straightforward thing to do. We were using averaging of gradients. So basically, we'd split a mini batch up into micro batches where they were trained on n workers. Each worker would process its micro batch, compute the gradients in the backward pass. The gradients would be shared, averaged, applied by all the models. It was synchronous. It wasn't fancy. We weren't doing async or anything like that. And then share that update back to the workers and go to the next step. And this worked. The models converged to similar, to a similar performance. But it didn't actually speed up much. It took many, many more iterations for the distributed thing to converge than for the sequential steps to converge. So we started digging into like what was going on, and our suspicion was like the zip code layer. So the zip code feature we knew from like the model trained sequentially one time was a very significant feature. Like the weights were important. Without that feature, the model did much worse. So it was definitely a significant feature, but it was input as an embedding layer at the input, right? So like what we suspected was happening was you have very non-uniform distributions of zip codes in the microbatches. So every microbatch sees like a very different number of like instances for a given zip code from each other. And when you propagate the gradients back from all the different layers and average the gradients kind of naively, you slow down how quickly you learn the weights in the embedding layer. The embedding layer starts to converge more slowly than even you're training sequentially and you're not averaging out what you learn for each zip code, right? Since the zip code feature is so important, that also slowed down like all the other layers downstream. Like they wouldn't converge until the embedding layer was like producing something useful out of them, right? So we tried a fairly simple prescription. This is not like any deep mathematics that supported this as the right way to do it, but we decided we'd try an alternative prescription. And all we did was during training, when we processed the samples, we would aggregate all of the input vectors for the zip code part of the input. So basically, it would be ones for the zip code that you've seen. And so, if you saw this zip code 5 times, it would be 5. Saw another zip code only 1 time, it would be 1. For all the other zip codes, it would be 0. And then after we ran the microbatch training, we shared the summed zip code vector back along with the gradient. And for all of the components of the gradient other than the embedding layer, we just average it like you would do for the standard gradient averaging. But for the embedding layer, we'd use these weights that we had collected as part of the microbatch training to average the gradients, to weight the gradients that were coming from each part. And the performance is still sublinear, but like with 8 machines, we were able to get to about, I think, 4 or 5 hours was what I remember for training. So pretty significant speed up, not entirely free in that like it was not, it was sublinear, so we were still like paying more to go faster, but it was definitely helpful for like iteration and for trying more things and so on. So the high level thing is like not much of the work was actually in the distributed infrastructure. So I think like in distributed deep learning, like the problems are not really infrastructure problems like they are in the they were in the MapReduce world and so on, where you had to do like Herculean things to like shuffle data or move data efficiently and be very clever about that. They're more about being clever in this reduce operation, like what exactly it means to collect data from the sub pieces and put them together. There's a lot of interesting work in this area that I recently, when I was reading stuff for this talk, I came across AdaSum, which is a new feature that's been added to Horovod, and it's distributed deep learning framework. The idea they have there is when you have gradients from the different parts, instead of averaging the gradients, you sum them, but you sum them in a way that you only sum the orthogonal components. In my mind, that like roughly comes out to taking the max over all gradients in each dimension, like each dimension max. It's not the actual math does something a little bit more sophisticated, because you project onto each other's, you project one gradient onto the other gradient, and then take the orthogonal component of the remaining gradient. So it's not quite just as simple as a max, because there's some addition in both dimensions, but it tries to avoid this problem of overstepping, but still going too slowly, right? So like when you average, you tend to like go too slowly in some dimensions because you're pulling them down with zeros, and other dimensions you make. So I think I think these kind of like solutions are going to be really interesting in unlocking distributed deep learning. I think it's actually different from like what we did for the embedding layer, because in this case, you're not taking into consideration the weight of the inputs. So you are doing something different for the averaging, but it's not sensitive to like what the input sample itself had in the microbatch. So something that maybe both will work together too. So the sort of like upshot of this is I think that the focus for distributed deep learning is shifting a lot from like the infrastructure space, where fairly simple things for infrastructure seem to work well. You spin up a couple of workers, all of them are assigned a GPU or a core, and they will do whatever work you assign to them. Telling them what work to do is fairly cheap and doesn't require moving a lot of data. Like you point them to their input data living in some disk, and data from there can move pretty quickly. So you don't need to do fancy things with I/O or serialization or things like that. What you need to be clever about is telling them what work to do. So what data to process, and then the really hard part is like how to combine the results from each of them in a way that preserves the convergence rate for training models and making progress without destroying the properties of the sequential algorithm, right? So like a lot of it is cleverness in that step. Sort of like the other direction, and I think this one is like kind of a little bit close to like work that like Colin is doing at Reality Engines and so on, is like instead of like trying to go faster on training one model, if you have a lot of computers, instead just do more kind of thing. And so we can use distributed computing without like much interaction between the workers for doing things like hyperparameter search, like start training models in over many different values of the hyperparameter, network architecture search, which I think Colin is going to probably give us a talk about next time or some point in the future. Do stuff with warm starts, which are useful in some cases, and so there's ways to spend computing resources other than going faster. You can do more work too, and that's another way in which like these distributed problems can be split up, and it's convenient because they are embarrassingly parallel, so you don't have to do a lot of heroics to make them work well together. So I'll end with saying like in my mind, I think we're fortunate that like deep learning has, where we are in deep learning is we don't have to actually worry so much about the infrastructure or the plumbing and so on for like getting distributed computing going. We can focus more on like the algorithms and the math and so on to make these distributed things work well together, which is actually a much nicer space. I think like working in the MapReduce space and all that is very constraining in terms of like the kind of computations you can do, because the framework is very rigid to achieve the kind of like scale it does. Whereas now we can like code in Python and do whatever we want, as long as we can be clever about like how we aggregate our results across our machines. I think actually as we're looking for new things, I think going back and looking at how stuff was done on supercomputers, or even now supercomputers are still used for weather modeling, all of them. So a lot of those frameworks I think have more relevant patterns to what you would need for like distribution and going faster with deep learning. And so that's a good place to look for ideas. I saw in like ring reduce and so on, which are these ideas used by Horowitz to like aggregate data, is actually stuff that's been used for a long time in supercomputers for like being clever about how you exchange data in like mesh grids for like computational fluid dynamics and so on. And then the last one, to the slide that was just before, is I think maybe we don't worry about taking more time at all and just like do more training and let computers do the model exploration, so that we have to do less of like the actual model search work ourselves, which is the direction of like simply network architecture search or other sort of auto ML type approaches, where we let the computers work for a long time on their own without our guidance, so that we can go do something more interesting. So that's everything I have.